The phrase "last line of defense" suggests certainty. It suggests a final shield that stands between the ship and destruction. In reality, on a modern warship, the last line is not a guarantee of survival. It is a trade between reaction time and judgment, between cost and consequence, between physics and probability. Naval defense is not designed around a single weapon defeating a single threat. It is built as a layered system constrained by time, geometry, magazine depth, and rules of engagement. Outer layers attempt to intercept early, when space and options still exist. Inner layers exist because outer layers are statistically imperfect. The closer the threat, the less time remains for deliberation. At that point, the system must convert uncertainty into immediate action. On February 25, 1991, in the Persian Gulf during the final hours of Operation Desert Storm, those constraints became visible. The Iraqi military detected a high-value target operating close to shore, the USS Missouri, a 50,000-ton battleship. From a concealed battery on the Al-Fao Peninsula, 2 HY-2 Silkworm anti-ship missiles were launched. The missile was not sophisticated. It was subsonic. It carried a large warhead and skimmed the sea surface to reduce radar detection range. It relied on simplicity and mass rather than elegance. When the missiles broke the radar horizon, the fleet did not have minutes. It had seconds. The SLQ-32 electronic warfare system detected inbound contacts. Chaff was deployed, creating a cloud of metallic strips intended to seduce radar seekers away from the hull. One missile diverted and crashed into the sea. The second remained locked and continued inbound. Operating nearby, the British destroyer HMS Gloucester engaged with Sea Dart surface-to-air missiles and successfully intercepted the remaining Silkworm. It was the first confirmed combat interception of an incoming anti-ship missile by another missile. On paper, the layered system worked: detection, soft kill deception, and hard kill interception. But layered defense does not remove friction. It redistributes it. 3 miles away, the frigate USS Gerald was also operating in defensive posture. Its Phalanx close-in weapon system was active in autonomous mode. The logic behind that configuration is straightforward. A sea-skimming missile traveling at high subsonic or low supersonic speed compresses the decision window to seconds. Human reaction time becomes a liability. The system must track, calculate lead, and fire without hesitation. Autonomy increases speed. It reduces delay, but it also reduces contextual judgment. When Gerald's radar swept the sector, it encountered the expanding chaff cloud above USS Missouri. To a fire control computer operating under time pressure, a dense, fast-changing radar return can resemble a terminal phase missile dive. The algorithm evaluated the data. The solution vector met engagement criteria. The system executed its programmed response. The Phalanx turret traversed. The barrels accelerated to approximately 4,500 rounds per minute. 20mm tungsten rounds were fired toward what the computer calculated as a threat. Several rounds struck USS Missouri's superstructure. No catastrophic damage occurred, but armor was penetrated and structural areas were hit. This was not mechanical malfunction. It was not malice. It was an interaction between sensor ambiguity, compressed timelines, and autonomous logic. The system did what it was designed to do: react faster than a human could. In doing so, it exposed the structural tension inside every automated defense layer. Speed without discrimination increases survivability against real threats, but it also increases the probability of false engagement when data is distorted. The 1991 incident is often framed as a near tragedy or a technological embarrassment. From a systems perspective, it is a case study in constraint. Sea-skimming missiles compress radar horizons. Electronic countermeasures distort returns. Multiple ships operate overlapping defensive systems with independent sensors and firing logic. Under those conditions, ambiguity is not an anomaly. It is normal. The lesson was not to remove close-in guns. It was to refine the architecture around them. Improve identification. Improve sensor fusion. Reduce the probability that decoys or friendly countermeasures trigger lethal automation. More than 3 decades later, the USS Gerald R. Ford represents the apex of naval engineering. Nuclear propulsion, electromagnetic aircraft launch systems, advanced power generation, integrated combat systems. Yet mounted on its deck is the same basic silhouette, the Phalanx CIWS. At first glance, this appears contradictory. Why place a Cold War-era rapid-fire gun on a $13 billion carrier designed for 21st century warfare? The answer does not begin with nostalgia. It begins with the reality that layered defense still collapses toward the inner ring when outer rings fail. The last line is not there because it is perfect. It is there because no other layer can fully eliminate uncertainty. The presence of phalanx on a modern carrier like USS Gerald R. Ford is often misinterpreted as institutional inertia. It is not. It is an acknowledgement that outer defensive layers are probabilistic, not absolute. Aegis interceptors extend the defensive perimeter dozens or even hundreds of miles. Electronic warfare attempts to seduce or blind incoming seekers. But no matter how sophisticated the architecture becomes, there remains a residual risk that something penetrates. The question is not whether the close-in gun can defeat every modern threat. The question is what role it plays inside the decision tree of naval defense. The Phalanx was born in the 1970s to counter subsonic and low supersonic sea-skimming cruise missiles such as Harpoon and Exocet. These targets travel roughly between Mach 0.8 and Mach 2 in terminal phase. At those speeds, radar tracking algorithms can establish a lead solution. The turret, capable of traversing roughly 115 degrees per second, can physically rotate into firing position. The engagement envelope is short, but not mechanically impossible. That design logic assumed relatively predictable trajectories. Sea skimmers fly low and fast, but typically along stable approach vectors. The fire control computer calculates a lead point based on velocity and heading. It assumes continuity of motion. Against a Mach 2 missile, that assumption holds long enough for correction loops to converge. The variable that has changed is not simply speed. It is maneuverability at speed. Modern hypersonic glide vehicles, such as China's DF-17 or Russia's Zircon-class systems, operate at Mach 5 and above. At those velocities, engagement geometry transforms from a tracking problem into a mechanical crisis. Consider a target at Mach 5, approximately 1,700 meters per second, within 1 kilometer of the ship. Time to impact is measured in fractions of a second. If that target executes even modest cross-range maneuvers, the angular velocity relative to the defending ship can exceed the turret's traverse capability. In simple terms, the computer may know where the target is, but the gun cannot physically rotate fast enough to align with the updated solution. The hydraulics hit their mechanical limit. The barrel lags behind the target's angular displacement. The system fires, but it fires into empty space. The gap between prediction and mechanical response widens faster than the correction loop can close it. There is a second constraint: predictive modeling. The Phalanx relies on lead point prediction. It extrapolates future position based on observed trajectory. Hypersonic glide vehicles are designed to degrade that assumption. Their terminal phase may include irregular, high-G maneuvers precisely to disrupt intercept calculations. When motion becomes chaotic within the engagement window, the statistical confidence of the lead solution collapses. Then there is the sensor domain. At hypersonic velocity, atmospheric friction can ionize air around the vehicle, creating a plasma sheath. Plasma interacts with electromagnetic waves. Depending on frequency and geometry, it can attenuate or distort radar returns. Even when not fully opaque, it complicates tracking fidelity. Electro-optical systems face their own limitations. Extreme heat signatures produce blooming effects. Atmospheric distortion at high temperature gradients can introduce jitter in image processing. None of this implies that hypersonic targets are invisible. It means that measurement error increases under conditions where reaction time simultaneously decreases. That combination is structurally unfavorable for a mechanically traversing gun with a short engagement envelope. Even if we assume ideal conditions, perfect tracking, stable lock, precise alignment, the physics does not automatically resolve in favor of the defender. A hypersonic vehicle carries enormous kinetic energy. If a 20mm tungsten penetrator impacts and fragments the missile at close range, the debris field retains forward momentum. Momentum does not vanish because structural integrity is compromised. At Mach 5, debris continues traveling toward the ship at near-terminal velocity. Instead of one intact missile, the ship may face a dispersed cloud of high-energy fragments, structural components, residual fuel, warhead fragments.
On the left,
the outcome depends on distance of breakup and dispersion pattern. At extremely short range, fragmentation may not meaningfully reduce damage to exposed systems. This is sometimes described as a kinetic trap. It is not a rhetorical device. It is a function of energy transfer. Close-in gun systems were optimized to destroy subsonic cruise missiles at distances where debris deceleration and dispersion reduced lethality before impact. Against hypersonic vehicles, the distance may be insufficient for that dissipation. From a pure physics standpoint, a rational engineer might conclude that a 20mm Gatling gun is misaligned with the upper tier of modern missile threats. And that conclusion would not be entirely wrong. But naval procurement is not driven by a single threat optimization model. The US Navy is not structuring its inner defensive layer exclusively around hypersonic glide vehicles. It is structuring it around the full spectrum of likely engagements, including the statistically dominant, lower-cost threats. The relevance of Phalanx today does not derive from its ability to defeat Mach 5 maneuvering weapons. It derives from a different variable entirely: economics. War at sea is not only a contest of speed and range, it is a contest of sustainability. Every ship carries a finite number of interceptors. Every interceptor has a unit cost. Every engagement consumes inventory that cannot be replenished at sea under combat conditions. In that environment, the inner defensive layer must be evaluated not only against hypersonic edge cases, but against the dominant pattern of daily threat traffic. Recent operations in the Red Sea illustrate this constraint. The Houthi campaign has relied heavily on relatively inexpensive drones and subsonic anti-ship cruise missiles. Many of these systems use commercial components, small engines, and simple guidance packages. Their unit cost can be measured in tens of thousands of dollars. Now consider the defensive side of the equation. An Arleigh Burke-class destroyer carries standard missile interceptors in its vertical launch system. The SM-6 provides extended range and advanced guidance, but its unit cost exceeds $4 million. The SM-2 costs over $2 million per round. Even the evolved Sea Sparrow missile approaches that scale. If a $20,000 drone forces the expenditure of a $2 million interceptor, the exchange ratio favors the attacker. If 10 drones are launched in a swarm, the defender may spend tens of millions of dollars in minutes. If 100 drones are launched over a campaign, the cost differential becomes strategic. War becomes a budgetary equation. The more critical constraint is not just cost per shot, it is magazine depth. A destroyer carries a limited number of VLS cells. Each cell used against a low-cost drone is one less cell available for high-end threats, such as anti-ship ballistic missiles or advanced cruise missiles that may follow. Inventory depletion can create a vulnerability window even if each individual engagement is tactically successful. This is the environment in which the Phalanx CIWS regains strategic relevance. A single 20mm tungsten round costs on the order of dozens of dollars. A typical engagement burst may require a few hundred rounds. The total cost per engagement can be measured in the low tens of thousands of dollars. the exchange ratio reverses. A cheap drone can be neutralized with ammunition that is even cheaper relative to the defender's high-end missile inventory. Phalanx does not preserve lives by elegance. It preserves inventory by volume. It clears low-end threats inside its engagement envelope so that Aegis and its missile interceptors are not forced to waste scarce and expensive assets on targets that do not justify them. This is not an emotional defense of a legacy system. It is a logistical one. The system acts as a filter. High-end interceptors remain in their tubes for high-end threats. The gun absorbs the economic pressure imposed by swarms. The 1991 incident demonstrated the risk of autonomous misidentification. The economic environment of the 2020s demonstrates the risk of financial attrition. In both cases, the question is how to reduce error without eliminating speed. The answer was not to remove the gun. It was to modify its sensory architecture. The Block 1B upgrade retained the M61 Vulcan cannon, but added a forward-looking infrared sensor integrated with the radar fire control system. Radar alone is vulnerable to chaff and sea clutter. Strips of aluminum foil produce strong returns. Breaking waves produce chaotic reflections. In isolation, infrared sensing adds a different dimension. A decoy cloud rapidly cools and disperses. A drone engine produces a sustained thermal signature. A missile exhaust plume radiates intense heat. By correlating radar tracks with thermal contrast, the system reduces the probability that a cold object is treated as a lethal inbound target. This does not eliminate false positives. It reduces them statistically. It shifts the probability distribution toward correct classification under compressed timelines. The infrared addition also expanded the system's utility against small surface threats. Fast attack craft operating in littoral environments present minimal radar cross-section and are often masked by wave clutter. From a radar perspective, the surface of the sea is noise. From an infrared perspective, a combustion engine stands out against comparatively cooler water, especially at night. Block 1B allows the gun to depress toward the horizon and engage small boats inside close range. The same correction loop that walks rounds onto an airborne target can walk them onto a surface engine block. The system was even adapted for land use during the Iraq War. Mounted on a heavy truck platform as the Centurion Sea-Ram, it intercepted incoming rockets and mortar rounds targeting forward operating bases. These projectiles are small and fast, but within a defined ballistic trajectory. The closed-loop tracking algorithm, simultaneously tracking the target and the outgoing stream of rounds, proved capable of adjusting aim in real time. It is not guessing once and hoping. It is measuring error and correcting it nearly 100 times per second. This closed-loop spotting is central to the system's lethality. The radar tracks both the inbound object and the ballistic path of its own rounds. If the stream drifts left, the system corrects right. The fire solution is continuously refined during the burst. In effect, it walks the impact point onto the target. In January 2024, the USS Gravely reportedly used its Phalanx Block 1B to intercept an inbound Houthi anti-ship cruise missile at close range after outer defensive layers failed to neutralize it. The engagement occurred within seconds of impact range. The missile was destroyed in the air. The ship survived. From a systems perspective, this does not validate the gun against hypersonic glide vehicles. It validates it against the statistically dominant subsonic cruise missile and drone threats that characterize many contemporary conflicts. But the system retains a structural weakness that upgrades cannot erase: ammunition capacity. The Phalanx drum carries approximately 1,550 rounds. At a firing rate of 4,500 rounds per minute, continuous fire would empty the magazine in roughly 20 seconds. In practice, bursts are controlled and shorter. Even so, saturation attacks impose arithmetic limits. If a swarm exceeds the system's engagement capacity before reload, the gun will spin dry. This is the next constraint in the chain. Speed was the first. Identification was the second. Economics was the third. Magazine depth is the fourth. And that constraint is already shaping what replaces the gun in the long term. Magazine depth is the constraint that reveals the Phalanx is not an end state. It is a bridge. A fully loaded drum holds roughly 1,550 rounds. At 4,500 rounds per minute, the theoretical maximum sustained fire time is approximately 20 seconds. In real engagements, the system fires in controlled bursts to conserve ammunition and refine aim through its closed-loop corrections. Even so, against a single inbound cruise missile, the arithmetic is manageable. Against a coordinated swarm, it becomes restrictive. If the adversary launches one missile, the gun engages, fires a burst, and likely retains the majority of its ammunition. If the adversary launches 10 drones in rapid succession, the system may need multiple bursts per target. If the adversary launches 20 or more, the defender must allocate bursts carefully or risk depletion before the final threats arrive. Once the drum is empty, the system is temporarily irrelevant. Reloading at sea under combat conditions is not instantaneous. During that window, the ship's inner defensive layer collapses back onto whatever missile interceptors remain. The layered architecture reverts to a narrower funnel. This arithmetic is why the Navy does not treat the gun as a universal solution. It treats it as a specific tool within a constrained engagement envelope. To address the gap between short-range guns and long-range standard missiles, some ships have integrated the rolling airframe missile system. RAM extends engagement distance to several nautical miles and provides a self-contained launcher separate from the VLS. Its interceptors are smaller and less expensive than SM-2 or SM-6, but more capable at range than a 20mm projectile. RAM does not eliminate cost concerns, but it reshapes the cost curve and expands reaction time. The evolution does not stop at missiles. Directed energy systems such as the Navy's laser weapon system demonstrations, Odin, and Helios represent an attempt to alter the economic structure of engagement entirely. A laser shot consumes fuel to generate electrical power, but its marginal cost per engagement can be dramatically lower than that of a missile interceptor. As long as the ship's power plant is operational, the notional magazine is limited by thermal management rather than physical ammunition storage. Lasers introduce their own constraints. Atmospheric attenuation, dust, spray, and turbulence degrade beam quality. Thermal blooming can distort energy delivery over distance. Power generation must compete with propulsion, sensors, and other ship systems. Cooling capacity becomes the new bottleneck. Engagement range is influenced by weather and line-of-sight geometry. No defensive layer escapes trade-offs. Against hypersonic glide vehicles, directed energy may offer advantages in speed-of-light engagement and reduced lead-time prediction requirements. But it must still maintain beam stability on a maneuvering target for sufficient dwell time to achieve structural failure. That is a different type of timing problem, not an absence of one. The Phalanx CIWS remains installed on platforms like USS Gerald R not because it defeats every conceivable threat, but because it occupies a specific niche in the layered defense matrix. It is optimized for close-range, low-cost, high-volume engagements. It is mechanically simple relative to missile systems. It can be maintained without consuming VLS cells. It preserves high-end interceptors for high-end threats. From a systems perspective, it is a risk management device. It reduces the probability that low-end saturation attacks drain strategic inventory. It does not remove the high-end hypersonic challenge. That challenge is addressed, imperfectly, by outer layers, by evolving interceptors, and potentially by directed energy. The 1991 incident exposed the tension between autonomy and discrimination. The Block 1B upgrade reduced classification error by fusing radar and infrared data. Modern operations have demonstrated the gun's continued relevance against cruise missiles and drones. At the same time, the physics of hypersonic maneuvering vehicles and the arithmetic of limited ammunition expose its boundaries. This duality is not accidental. It reflects institutional decision-making under constraint. The Navy cannot optimize every ship exclusively for the most advanced threat. without bankrupting its ability to operate daily. Nor can it ignore high-end adversaries in favor of cheap drone swarms. Layered defense, therefore, is not about building a perfect shield. It is about distributing imperfection across multiple systems so that no single failure becomes catastrophic. The Phalanx is loud, mechanical, and visually archaic compared to electromagnetic launch systems and advanced radar arrays. Yet it persists because it satisfies a narrow but critical requirement. Convert a low-cost projectile into a statistically acceptable probability of intercept inside seconds without consuming strategic missile inventory. It is neither obsolete nor sufficient. As adversaries continue refining saturation tactics and maneuvering high-speed weapons, the pressure on inner defensive layers will intensify. The future architecture will likely integrate guns, short-range missiles, and directed energy into a tighter sensor fusion framework, attempting to reduce classification delay while expanding effective magazine depth. The central question is not whether the gun survives, it is how the balance between cost, speed, discrimination, and endurance will be recalculated as the threat spectrum continues to widen.